moved back to China. She's not very happy about it. So we have to try to get you back to San Jose. Tina.
Hello? Hello? Okay, sir. Hello and welcome to my presentation about IPv6 young models, a subject which is becoming critically important to the transition process. Let's start by looking at some background information, which I hope will help you understand why the deployment of the young models is so important. Oops, did I click something wrong? Wait a second.
Is that the Ying model?
Yeah. Should I just... Yeah, okay. First, as we all know, IPv6 adoption continues to accelerate. The percentage of users that access Google over IPv6 hit 6% this month. The transition is still in its infancy, but at this rate, the population will reach double-digit percentage points later in 2015. When we look at the global map, we use that IPv6 adoption rates and the quality of user experience varies by region. The lowest adoption rates and the worst user experience are in Africa, which the highest are in the America and Japan. In between are China and Europe, with the exception being Belgium. Congratulations, where adoption is the highest. Clearly, we have a lot of work to do to improve the user experience around the world. But we think deploying a simplified use of policy automation will help. Automation abstraction will help. There is saying necessity is the mother of invention. This holds true in the IPv6 transition deployment of new technology is being led by companies that are driving the most native IPv6 traffic. Companies are like YouTube, Netflix, and Facebook, who deliver massive amounts of content to billions of users. It is hyperscale growth which motivates these companies to invent ways to make the transition more automated and efficient. But in spite of some incredible technologies which has been deployed by the largest cloud providers and carriers, deploying IPv6 services remains very complex. Configuration is complicated. IPv6 VPN provisioning is time-consuming, and as well, time is money. And it's still very difficult to upgrade IPv6 transition technologies in flights. SUPA and IPv6 service young models are going to fix that. In summary, while IPv6 transition tools exist, new issues are emerging. Operators need various types of IPv6 transition technologies depending on performance requirements, deployment scenarios, etc. To address these difficulties, a software-defined unifying approach is needed to provide a unified way to deploy the IPv6 in a cost-effective, flexible manner. The solution is technologies which, like Clark Kent changing into a Superman, will enable customers to implement an agile transition to IPv6. The name for such a technology is simplified use of policy abstractions, or SUPA. And yes, this is Superman. The goal of this simplified use of policy abstraction group is to develop a methodology by which network services can be managed and automated by using a set of standard policy rules. And the YANG-based services and the policy data models. SUPA will focus in the first phase on the inter-data center traffic management as part of the distributed data centers, including the automated provisioning of the site-to-site virtual private networks of various types. SUPA introduces the concepts of multi-level, meaning the multi-levels of abstraction and multi-technologies, for example, IP, VPN, and MPLS network abstraction, to adjust the current separation between the deployment and the development operations. Multiple levels of abstraction enables the common concept presents in different technologies and implementation to be represented in a common manner. This facilitates using diverse components and the technologies to implement the network service. The following standard generic YANG-based service and policy data models are within the scope of SUPA. A model of the network services, for example, VPNs, and the network resources required by the network services to be correctly deployed and executed on the physical or the virtual topology. And a model of the policy rules for mapping the network services and mapping services dynamically to the network topology and network resources. SUPA will define the network management, application-based policy protocols, mechanisms, and models required to map the application's demands to network management policies and procedures. For example, the traffic redirections based on the customer's grade and link status, which can directly enforced by a network management system on network devices to meet the operator's needs and demands. The network applications in OpenV6 case needs to manipulate the network to achieve its service requirements. Various IPv6 transition mechanisms, for example, Lightwave 4/6, MAP, etc. We just got a bunch of RFCs published from IETF Software Working Group, are considered to be a variety of applications in OpenV6. SUPA configures the OpenV6 policy information, for example, the flow tables, in the network management application in the form of network configurations models. The flow table is used for handling the incoming packets for the forwarding node. The flow table can be updated by the application based on the user requirements. If an incoming packet does not match any entries of the flow table, the packet will be delivered to the controller for generating new entries. To give you an idea of what types of real-world events can be defeated by the SUPA apps in OpenV6, I would like to share with you the 9 use cases which are excerpted from draft from IETF. A link to the paper is under the title of this slide. It's the Draft Soon SUPA OpenV6 use case from China Telecom. Use case number 1 for SUPA applications in OpenV6 is evolve from one scenario to another. Using the IPv6 transition period, the networks need 3 stages of IPv4 only, dual stack, and IPv6 only. The networks should support both IPv4 services and IPv6 services at the same time at each stage. There are multiple IPv6 transition technologies for different network scenarios. For example, IPv4 network for IPv4, IPv6 user access. IPv6 network for IPv4, IPv6 user access. IPv4 servers for IPv6 visitors. Excuse me, I'm losing my voice. Yeah, I need my Superman to rescue me too. Different network scenarios will coexist during IPv6 transition, which means the IPv6 transition device should support multiple IPv6 transition technologies. Finally, as you can see, there are 6 possible scenarios in the IPv6 transition period. Use case number 2 is multiple transition mechanisms coexist. In transition from one scenario to another, different transition mechanisms may have different impacts on user experience. For example, DS Lite will have some impact due to adjust sharing compared to the 6RD mechanism, and Net64 will have actual impact due to the ARG issues. Operators will need to offer a fallback mechanism to guarantee the same level of user experience when there are complaints from subscribers. Therefore, it is required to support multiple transition mechanisms in the same area, even in the same device. Another use case is that multiple scenarios may exist in the same stage. For example, if there were both IPv6 only devices and IPv4 only host in the same area with limited public IPv4 addresses. Both Net64 and Net44 or DS Lite are required to achieve the IPv6 service connectivity. The current implementation normally uses a separate instance for each mechanism, and additional policies need to be applied when running multiple mechanisms in one device. Some have a limitation on the numbers of policies which can be configured in one device, while some have restrictions regarding the resource occupation. For example, one transition instance will occupy a static amount of memory. The major requirements in multiple transition coexistence mainly lie in 2 aspects: the need to implement different IPv6 transition technologies in the same hardware, and the need to support this by upgrading the network devices as little as possible. The need to hop over legacy infrastructure, which are not IPv6 enabled, costly or impossible to upgrade. Use case number 3 is scatter address pool management, or herding cats. They are not cats, some wild animals. When operators are facing with address shortage problem, the remaining IPv4 address pools are usually quite scattered. It is quite complicated for an operator to manage scattered address pools in many transition devices. The situation will become even worse when multiple transition mechanisms in the same device need to be configured with different address ports. Besides, since the occupation of the address ports may vary during the different transition period, for example, when there is not many IPv6 enabled services and IPv6 enabled devices, IPv4 traffic will still occupy a great portion of the total traffic, while in the later stage of IPv6 transition, IPv4 traffic will decrease and the amount of IPv4 address ports are decreased accordingly. The ideal way is to manage the address ports centrally. Different transition mechanisms can require the address ports on demand. For example, when one transition mechanism is running out of current address ports, it may request an additional address port. It can also release the address ports that it is not using anymore. In this way, operators do not need to configure the address ports one by one manually, and it also helps using the address ports more efficiently. The major equipment and requirements are the management plane should have the ability to configure the address ports for different mechanisms centralized. The management plane should be able to send the addressed port information to the transition devices. Use case number 4 is virtualized computing resource management. IPv6 transition mechanisms, for example, DSLi, CGN, etc., consume a lot of computing resources to maintain a large number of session tables. Because the number of concurrent subscribers varies over time, managing the computing resource centrally is better. For example, we had add more computing resources when needed and release back to the resource pool if not necessary. The major requirements for the management plan is it must be able to allocate and withdraw the computing resource for certain V6 transition traffic, request more resources for certain V6 transition traffic. Yeah, let's
And
pass.
Tina, you have only 3 minutes to go.
Yeah.
Will not be 9 cases, huh? Maybe choose the next best one.
Okay. And use case number 5 for SILPA application in OpenV6 is transition interface to third-party apps. Use case number 6 is ICP app out of transition mechanisms. Use case number 7 is failure models for transition mechanisms. Use case number 8 is failure mode for native deployments. You see the happy eyeballs. And our final use case is number 5, the app-driven opt-out mechanism for ISPs. Hopefully, you agree there are many use cases for SILPA apps in OpenV6. Now let's look at the technology behind SILPA and how it works, starting with the architecture of intelligent IPv6 controller. With an intelligent IPv6 controller like this I show, customers can convert simple YARN models into complicated device configurations. With a long list of capabilities, the YARN models also customize, like a flexible deployment by being able to support the physical devices and an SDN controller, as well as device and network multi-layer deployment. Another benefit is friendly dev environment, which supports multiple programming languages, Java, C, Python, and a simple development environment with improved tools. The controller also provides broad interoperability with multi-layer open APIs and integration with multiple cloud management platforms such as OpenStack and Microsoft OpenEye. Here is an example of Young model in OpenV6. It contains basic information about tunnel, translation, and mapping rules among them in the OpenV6 use case. This page shows the IPv6 service model. It contains the information of tunnel, translation, and mapping rules. This is a full table. All of the OpenV6 services can be abstracted via this model. Here is another example of Young models in OpenIPv6. In step 1, a user-defined policy received by the service management is a high-level abstracted policy. For instance, if a certain event occurs, some objects may require configuration changes. In step 2, the SM translates the high-level user-defined policy to a more concrete policy and sends all the new policies to the controller. In option A, the IPv6 service data model describes an IPv6 service. It contains basic information about tunnel, translation, and mapping rules. In this option B, the policy data model defines the starting, stopping, renewing policy rule. This will be used to change the configuration of affected objects. This enables the attributes can be used to starting, stopping, and rule. When name exists and the enable is for enabling, the data will update an existing policy. Then in step 3, the controller generates the issue and issues device-specific policy rules, for example, tunnel configuration to affected network elements. So this concludes my presentation. I'd like to summarize by saying we are only at 6% adoption, so we have a long way to go. But deploying IPv6 services remains very complex. So customers need a software-defined, unified way to deploy the IPv6 in a cost-effective, flexible manner. SILPA is the answer. A platform ideal for addressing a wide variety of transition use cases. I invite you to learn more about Young-based service and policy data models by visiting SILPA. Thank you very much. If you would like to contact me in the future, email me tina.zhou.zhouting@huawei.com. Thank you.
Thank you. Keynotes don't need questions because that would be way over the time allocated. I would like to ask Mark to come in. Thank you, Tina. Well, for the sake of gender parity, so I let you